Welcome to the Imperial Truth. I'm your host, Eric, and today we are going to do something a little different. We're going to talk about sort of the science behind some of the lore of the Horus Heresy. And I'm doing this in part because I'm sort of trying to branch out away from just talking about the rules in the game or the narrative play in the game, though we're going to continue to do those things. But I'd like to, talk about lore and other aspects of this and bring maybe a slightly different perspective of these things into the sphere. And so in my day job, I'm a scientist. I do geology and microbiology. And I have recently reread the first four books of the Horus Heresy because, with the third edition version of the game, that was sort of the perspective. And we have this new book, Drop Site Massacre, which sort of follows up on what's happening on Istvaan V, which is I'm about two-thirds of the way through. It's a great book, by the way. And yeah, as I reread those, I started thinking about some of the things that are happening and imagining what we could talk about in this context. So we're going to talk about virus bombs in the Horus Heresy and sort of the science behind them and try and get into a little bit of this and maybe educate everyone a little bit about this stuff. So I hope that you enjoy this. If you do enjoy this sort of content, please like and leave a comment. Subscribe if you're not subscribed already. We're coming up on 400 subscribers, which is pretty fun. I think we have like 11,000 play hours of videos, which is just blows my mind that people are that interested in what we're saying, which is great. I love it, and I appreciate it. And keep it up. You guys are doing great. So let's get in and let's talk about this. So we're going to have to talk a little bit about the science and some of the terminology as we go. But I am an educator, so we'll do our best to educate you in a way that is um, uh, uh, accessible for you. So pathogens, and if you are a microbiologist, please don't come at me too hard because some of these things are a little simplified for this context. So bear with me on this. So a pathogen is an infectious agent that can cause disease. We'll come back and define disease in a minute, but for our purposes, we can divide them into roughly five categories because we're talking about infectious disease here. There are genetic diseases and there are environmental diseases, and there are diseases that are combinations of all of those things. But if we're talking about infectious agents, specifically not using the term like living organism, we have prions, which are just proteins that are misfolded. And these bump into other proteins and cause them to become misfolded. And this can cause sort of a cascade of protein misfolds across an organism. The ones that you're probably familiar with are mad cow disease or bovine spongiform encephalopathy, which is the original or the real name for it, or Crutchfield-Jacobs disease, which is the version that can affect humans. So if we eat cows that are infected with BSE, those misfolded proteins can make their way into our brains and have bad effects on us, very, very bad effects on us. If we eat other humans, we need their brain matter, and if they were infected with CJD, we could also get that. There's another form in the United States right now that is, I forget what it's called, but it affects deer, and I really should remember this name. But if you are a hunter and you hunt deer, you in Ohio, where I am located, you have to get your deer checked to make sure that they are not infected. It's a big deal. Yeah. So above viruses and sort of complexity, we have above prions in terms of complexity. We have viruses, which is where we'll spend a lot of time today. So these are infectious agents. They're not necessarily alive. There is debate of whether or not they're alive. And they replicate using the host of the organism. So viruses don't have a metabolism. They can't replicate on their own. They need to infect another cell to replicate. So the influenza virus, the flu, is an example of this, or coronavirus like COVID-19. Not that I'm shooting to get like banned by YouTube, but we'll mention that. That's one that you're almost certainly familiar with. If we sort of increase our complexity a little bit, we have bacteria. These are living organisms. There's no doubt about that. They are prokaryotic organisms, which just means that they don't have organelles. So you and I, we have different compartmentalized rooms within our cell that we do different things. And bacteria do not, I mean, they tend not to. There are bacteria that have organelle-like structures, but they tend to just kind of do everything sort of in the body of the cell rather than in specific organelles. Because of this, that gives them a lot more freedom to replicate much faster, and we'll talk about that today. Bacteria you may be familiar with are Vibrio cholera. So if you've heard of a cholera epidemic, that's the one that causes that. Or Clostridium difficile, commonly called C. diff in the medical community. This is the one that if you've ever gone to visit your aging grandparent in a nursing home, and the nursing home has an especially a rank smell to it, this is probably what's causing that rank smell. Fungi can infect humans as well. We're familiar with like yeast infections or athlete's foot. These are eukaryotic organisms. They're much more closely related to us than they are to bacteria. And then there are animals that can infect us, like tapeworms or brain-eating amoebas that can also infect us. So hopefully that gives you sort of a perspective of the types of organisms that we can have. In terms of additional terminology, disease for today, we're going to call that to be any loss of fitness in the host. Now, fitness is a wide definition, but let's just say that if it causes you to not be able to do things you previously did, that's a disease. That's causing a loss of fitness. Virulence is our medical term for how infectious of a disease it is. So the pathology of the infection. A highly virulent disease will spread really easily and very fast. Case fatality rate, by comparison, are deaths per year, deaths per infected person. So we calculate the total number of infected persons, and then we calculate how many of them died. That gives us our CFR, case fatality rate. So we could have a disease that's very virulent that everybody gets, but very few people die from. Or we could have a disease that's very hard to get, but has a really high case fatality rate. So like rabies would be an example of that not a lot of people get rabies, but those that do, I think it's got like 100% case fatality rate. So that's not a great thing to have. Our vector is our method of transmission. So if we are thinking about something like malaria, that's transmitted via mosquitoes. Influenza is transmitted via droplets, usually from our sneezes or our coughs that get into other people. We could have something like C. diff, which is transmitted via my favorite pathway, which is the fecal oral pathway, which means you're literally accidentally ingesting fecal material from somebody else. Yeah, so we can have lots of different vectors for these things. Incubation period is the latency between when we have exposure to a disease and when we are showing symptoms. So it's the amount of time it takes that disease to sort of ramp up in the host so that we can notice that we're sick. Are not, I know I'm just spitting these out, but we're going to use these terms as we go. So I apologize for kind of dumping them on you, but hopefully you can always refer back to this slide if you need to. So R naught is one that has popped up a lot in the last few years. It is the measurement of how fast a disease spreads. So an R naught of 1 will infect 1 person for every person infected. An R naught of 2 will double. So every person that's infected will infect 2 people, and so on and so forth. So an R naught that's below 1 will tend not to spread. An R naught that's significantly above 1 will spread really rampantly. It'll spread quickly. And then doubling time is the amount of time it takes to double the number of infectious particles in a host. So if we are infected by 1 bacterium, the amount of time it takes to go to 2 bacterium, or from 2 to 4, from 4 to 8, etc., that is our doubling time. And again, that'll come into play in just a little bit. So those are our terms. Kind of get those set in your head, and we'll start talking about virus bombs and sort of how this works. So this is basically how viruses attack cells. So viruses are particles. They have these components on the outside of them that you can think of like keys. If you are familiar with the influenza virus, we sometimes have like the H1N1 or H2N5 or some a combination of those weird letters. When you get your flu vaccination, you are getting, I think, three of the most what we think are going to be the most infectious versions of the flu for that year. And the flu vaccine essentially teaches your body that the flu keys aren't right. So the H1N1, I think the N component there is the part of the key for this. And basically they attach themselves to your cell. They turn that key against your cell, and your cell is like, hey, this is an okay thing to let into to us. So your cell will then accept what the influenza virus is putting in, or whatever the virus is that you're being infected by. Once inside the cell, that particle, that viral particle, will release its genetic material, usually, well, not usually, sometimes DNA, sometimes RNA, two different types of genetic material. And then the mechanism of your cell, the kind of the machinery of your cell will pick up that genetic material and start to replicate it. And that genetic material will basically commandeer your cell's mechanisms to allow it to produce more viral particles. And then your body will very kindly export those viral particles back outside of your cells, where they will infect other cells, which will then produce more viral particles, which will then be released into your body and produce more viral particles, right? This process continues until you are infected. When your body figures out that you're sick, then you'll start to produce antibodies that sort of identify those viral particles as being bad, and you can hopefully get resistance from that. So that's sort of that process. The important things to understand here are that the virus itself is not replicating. Your body is replicating the virus. It's duplicating the virus. And so the speed of replication is limited to your body's capability to reproduce the virus, which is not a fast process, as we'll see in a little bit. It's in humans. This is at the very least a few hours, which is a problem if we're trying to virus bomb a planet, because we maybe want this to be a little bit of a faster process. So in our Istvaan III bombing, so in our, I'm trying to remember the book, it'll come to me. Galaxy Burns, I think is the one. Very good book. We basically have this sequence. So they shoot multiple warheads, hundreds, if not thousands of warheads that explode into the atmosphere. I'm assuming that the idea here is to have some sort of aerosolized transmission. So some sort of transmission that is sort of happening in the atmosphere and can be inhaled then. And then they also fire warheads at ground level. And I don't understand sort of what the context of this is, except maybe to increase the localized particle density. So maybe you shoot the aerosolized warheads across the entire planet, but then the specific location that you want to bombard, you fire warheads at the ground. Regardless, the vector of transmission seems to be, in the story, it seems to be respiration. So breathing it in definitely gets you infected, but also contact to the skin seems to. It talks about people getting lesions and open sores on their skin when they come into contact with the virus, which we'll talk about in a little bit. It very clearly and repeatedly talks about it liquefying flesh. So liquefying flesh is just accelerated putrefaction, which is a word that people in the wargaming community get wrong all the time. So putrefaction is basically accelerated decay. So it's that process by which we break your organic molecules down, your organic cells down. I'm trying to be very careful about my terminology because chemistry and biology have same words for different things, but would break down your cells and the integrity of your tissues and things like that, basically turn you into soup, which would be just your kind of like broken up carbohydrates and fatty acids and things like that, kind of chopping them all into smaller bits, so that you essentially fall apart. The virus also eats through organic polymers. So they talk about it eating through the seals of armor, which I'm assuming are organic polymers in the story. I don't know that they're ever called out as that, but something like plastic would be an organic polymer. So that just means that we are using carbon bonds, carbon and hydrogen bonds, to kind of produce these long chained molecules that we then weave together to form structures. So you and I, we can't eat a plastic water bottle or a plastic bag or a miniature, but those things are still organic molecules from a chemical perspective. And there are organisms that can digest that stuff, but we'll talk about it in a minute. Viruses cannot. So that's a little bit of a problem. And all of this seems to happen over the course of seconds to minutes. Even in the book Galaxy Burns, it's not consistently written sort of how long this process takes, but it's no more than minutes from the time that they sort of see the first bombs hitting the atmosphere, that people start dying. So this is a very fast process. And so again, I know this is a lot to throw at you, but we'll kind of keep that in mind as we move forward with this discussion. So if we compare different viruses that we have today to kind of get a perspective of these things, so measles and mumps are sort of tied as some of the most the most virulent of our viruses. Measles and mumps both have an R naught of about 12. So that means for every person, 12 means, yeah, I have that written right. Sorry, I panicked for a minute. That means for every person infected, 12 additional people on average will get infected, which is an absolutely astronomical R naught, because that means that your patient zero infects 12 people, and then those 12 people, they infect 144 people. And I'm not good at math, so I can't tell you what the next number in that sequence is. But you can see how that's sort of an astronomical acceleration of that virus, which is why it's so important to get vaccinations against like the MMR vaccination when you're a kid, to prevent these things from passing from person to person. But even an R naught of something like 3 or 4 can be really devastating, because they will pass around to a large portion of the population. Incubation period is the amount of time it takes for our virus to go from being a person from being infected to having symptoms. And the fastest I could find for this is poliovirus. And this is really important because this incubation period is 4 to 6 hours, which is a long time considering our virus bombing is supposed to kill people in minutes. So that means from the time that you're infected to the time when you first show symptoms, not when you're dying of it, when you first show symptoms, is at most 4 hours. Why is it so low? Well, it's so low because remember, those viral particles have to infect your cells, and then they have to rely on your cells to reproduce them. And then they have to build into a sort of a concentration where you begin to feel sick. That process takes time. And we humans, our metabolisms are not, they're not bad, but they're not super fast in terms of this. Now, maybe for a genetically engineered space marine with a faster metabolism, they might, with better regeneration and stuff, they may have a faster reaction to these things. But then we also have to consider that they have a stronger immune system. So, I still think 4 to 6 hours is sort of maybe the upper limit for sort of an infection of this nature. In terms of case fatality rate, that is the number of people that die versus the number of people that get infected, rabies is at the top of this list at 100%. There are several viruses that you can get infected by where basically when you get infected, you will die at some point. But it's worth noting that a lot of these, it is often months to years later. It is not There's not a lot of viruses where you get infected and then 6 hours later you are dead. There's a bacterium that can do that. We're going to talk about that in a little bit. But we tend not to have that with our viruses. Also, human infecting viruses tend not to liquefy our hosts. Thankfully for us, there aren't any viruses that I know of where if you get infected by it, your body dissolves. That would be bad. Um, so yeah, we don't have any sort of measurement in science for this sort of science fiction-y type thing. So there are some additional complications, and we're going to, on the other side of this, we're going to talk about how this could actually happen. So I'm not going to completely shoot it down, no pun intended. But there are some additional complications, and one of these is just evolutionary pressures. The more complex we make a system, the slower the replication rates are going to be. So infecting humans is really difficult because we're going to have slower replication rates because humans are bigger. We reproduce our cells a lot more slowly than other organisms. And while we may start to produce a viral load in our body, which is the number of viruses that you're carrying, those things tend to happen a little bit more slowly than in maybe another organism like a bacterium. The greater our virulence, so the more sick you get, typically means lower transmission rates. So, for example, if you get the flu and the flu is so bad that you can't go to work, well, then you're not infecting those people at work by sneezing and coughing on them. So, a good virus, quote unquote, from the virus's perspective, wants to reproduce just fast enough, sort of bumping up against that upper limit where you don't actually feel very sick. And then you will transmit to a lot of people. Now, they don't think about these things, but if we're thinking about evolutionary pressures, that's where we're pushing this. And all viruses and bacteria, they're going to mutate. They do mutate very quickly. In fact, viruses are very sloppy when they put together their viral particles in your cells, and they'll pick up other pieces. That's why we're worried about things like swine flu or bird flu jumping over to humans, is because the virus, when they kind of if you have two viruses in your body at the same time, when a viral particle is put together, it can sometimes just accidentally pick up another virus's genetic material, and now you have a new version of that virus. And so viruses and bacteria, they mutate very quickly, and they're going to move away from anything weapons grade within a few generations, because again, we either want to have really high virulence and kill the host, but reproduce really, really fast and produce a lot of additional pathogens, or we want to keep our virulence low, not make people very sick, but transmit a lot. And so bacteria and viruses aren't necessarily going to stay at that state that we're like weapons grade. Now, are there genetic markers that we can put in there, or like 30,000 years in the future, could we have accelerated our ability to manipulate genetics? Yeah, I mean, that's exactly what we're going to talk about in a minute. But from, evolution has been working for, billions of years. So we're still not going to be able to erase that component. Also, we have this idea of time constraints that's a little bit of a complication. So again, in the story, people are dying in seconds to minutes. We don't have people sort of kicking around on the surface for long periods of time affected by the virus. It does specifically call out the fact that it infects everything on the planet and liquefies everything and sort of breaks down all the things almost instantaneously. And there is no organism that I know of that I can come up with that kills as quickly or efficiently as what's in the novels. It's not even close, right? We're talking about going from being alive to being dead within minutes. The best I can do, we'll talk about it in a little bit, is hours, which I think is still a compelling argument to be made. But yeah, it's just too fast. Just the incubation period, just getting into your cells and reproducing, if you're a virus, is going to take time, and that's not going to happen in seconds. And like I said, the process of DNA or RNA transcription is it's slow. It's limited by the host, not the disease. It doesn't matter how fast we turn up. the disease, if we're infecting you with a virus, it's your body's rate of replication that's going to control how fast that virus spreads. Yeah, and then the last problem is that viruses don't eat anything. They don't have a metabolism. We mentioned that earlier. So they're not going to eat through armor seals. We would need some other agent to eat through our armor seals and break through those barriers. Even to cause skin lesions is going to be really difficult. There are viruses that can be transmitted skin to skin, but it's not the majority of them. And usually you have to have some sort of fluid transmission in that. So you'll have to have like an open sore already before you can get that infection. So there are some complications with this. But there are some organisms that are sort of viral bomb-like and worth noting. And one of these is this Baculoviridae, which is a virus that specifically targets arthropods. So like spiders, ants, caterpillars, things like that. And in the last stage of infection, it does lyse the host cells. So lysing the host cells means it takes the cells from being these sort of balloons where the inside of the cell is on the inside, and then we've got a barrier for our balloon, and then we've got the outside of the cell. Lysing is where we pop the balloon and all the guts come out and go everywhere. That is literal liquefaction or liquefaction. We can see this here. There's a caterpillar in the image, and then the one on the top, that's a liquefying caterpillar. And that is very similar to what we see with our, or what we see in the novels. So if you could take a bacteria, or sorry, a virus like this, and manipulate it so that the components that liquefy the cells could infect humans, that would be a really, really awful way to go. And in fact, we already genetically modify this organism and release it to control insect pests. So we've already kind of utilized this in a role in the second millennium to combat insect pests. So the idea of taking something like this and taking the genetic markers that do the liquefaction and inserting them into some other organism it's not unreasonable. It's horrifying to think about, but it is an example, a nature of an organism that does what we see in the books. The other side of things is this replication rate that we see in the books that is really, really high and sort of almost unrealistically high, probably unrealistically high. And I point this out because E. coli has the fastest doubling rate of any bacterium that I'm aware of. And because viruses are tied to the host organism, we don't really think about them in terms of like replication rate. They're not doing the replication. The organism is, the host is doing it. So E. coli reproduces every 15 minutes. And it does this by basically having multiple. So like if you think about replicating a cell, is you have to copy all the DNA, you have to copy all the instructions. You have to have two copies of the DNA before you can split. Well, the time it takes to go from the beginning of your DNA to the end of your DNA and copy it all, that's pretty extensive. DNA is pretty complex, even for something as simple as a bacterium. The way E. coli gets around this is E. coli has multiple duplications of its DNA happening at the same time. So if you just pause, like if you froze an E. coli cell and pulled out its DNA, it would have the original DNA that's doing the life of the organism, and then it would have a duplication already in process of that DNA. So you have making copies of that, and then it's already sort of in the next generation of making copies of the copies for the next split. And so it's already two replications ahead before it even starts the process of splitting into two cells and reproducing. This allows it to reproduce at about 15 minutes of its maximum replication rate, which means that you have one cell, 15 minutes later, you have two cells, another 15 minutes later, you have 8 cells, another 15 minutes later, you have 16 cells, right? And so this replication rate is really sort of exceptionally high. So basically, if we allow for infinite growth, unlimited food and water, no pollution, sorry, not pollution, no pollution, everything. So we're taking off all the growth parameters, everything that would limit growth, and we just use that replication rate. In 36 hours, that one cell that is the weight of like a picogram, I think is their weight, is greater than the mass of Earth because it's replicated so much. And so that sort of replication rate is really astronomical and allows us to have sort of those maybe not killing you in seconds, but definitely going from being not infected by this to being feeling the infection within minutes. If you utilized replication rate like this, which is in a bacterium, not a virus, which is going to be important in a minute, you could have some infectious agent that was really, really bad, and would reproduce really fast inside the host. But again, you have to step away from viruses to sort of get this. The last thing we're going to talk about before we sort of set up what I think it is maybe a better explanation of this and a more scientific one is this idea of after everything has run its course and the entire planet has died, which is, we'll talk about in a second, isn't even really feasible, that all of that excess gases, I think they call them the funerary gases. So I'm guessing they're thinking about oxygen and methane, which is what I'm going to grab here. Then we shoot the planet with a lance strike and the atmosphere ignites and everything burns and there's this huge massive explosion. And it's a really great moment in the book, and I'm not poo-pooing that at all. I do love the Horus Heresy books because they are so grim and dark and crazy. But just as a sort of example, on Earth, which is the planet with the most life of any planet that we've ever found, we have about 2,500 gigatons of organic carbon on Earth. Now, there's an asterisk here because only about 500 gigatons of that carbon is locked up in animals and plants. Most of the carbon, the organic carbon on Earth, is locked up in soils, which are going to be really resistant to any sort of virus or bacterial bombing. They're going to, even a meter or so under the surface of the soil, you're going to be pretty unlikely to be able to access them via any infectious agent. We also have to consider that a lot of this organic carbon is in the oceans, and at least on Earth, we have a lot of organic carbon in our deep oceans. And so most of this organic carbon isn't going to be accessible to our virus bomb, the vast majority of it. But let's pretend it is, right? So we're gonna pretend it's all going to get consumed. On Earth, we have about 1 million gigatons of oxygen in our atmosphere and about 5 gigatons of methane in our atmosphere, which is a gas that is produced by living organisms and decaying organisms, which is very flammable. Methane is the key ingredient in natural gas. So we're going to make one assumption already, that all of our carbon is going to get transferred through this process, which is not, but we're going to pretend it all will be. And we're going to pretend that all of our organic carbon is this sugar molecule, C6H12O6. This is a very simple sugar. It's sort of the model sugar for the photosynthesis respiration reactions. It's not. Even in your body, we have a lot of complex sugars, and that's complex organic carbon molecules, and that's not even to say anything about plants with cellulose and lignin and things that are really resistant to decay. But again, we're going to assume it's all sort of one of the most easily accessible organic carbons. This would, if we converted 100% of our C6H12O6, or let's assume 2,500 gigatons of it, into oxygen and methane, we would get about 1,250 gigatons of oxygen out of this, which versus the 1 million gigatons of oxygen that's already in the atmosphere isn't really anything. It's 1/1000th of the existing oxygen. So that's not going to really make the atmosphere more flammable. Adding an additional 625 gigatons of methane would definitely make a difference, but it's not going to make that big of a difference. It's not going to be like now we can light the atmosphere on fire, especially across an entire planet. You may be able to, if you had one population center, sort of have everything die instantaneously, release all their gases. Maybe in a population center, you could do it. But again, it's just not going to happen. And it's really sad that the mathematics don't work out on this because it's such a great moment. But there's just not enough flammable material with regard to our overall atmosphere that's going to be ignitable. More interestingly, I think, is the idea that during the KT extinction, so the Cretaceous mass extinction, which was when an asteroid basically the size of Mount Everest hit Earth. In the aftermath of that, the atmosphere, it didn't catch fire, but it was so hot from that from all of the ejecta that was into the atmosphere. So as this asteroid the size of Mount Everest hit the Yucatan Peninsula, it basically vaporized this rock, and that vaporized rock got thrown everywhere. And that ejecta cloud was superheated and got so hot that it caught basically every forest on Earth on fire, created a worldwide firestorm. And that firestorm we can see in the fossil record, which is pretty crazy. So the thing is, we could create a firestorm and we wouldn't even need to kill everything to do it. In fact, I would imagine this is sort of what a cyclonic missile does. When we think about that, is that it's not so much that they're destroying the crust of the planet, which would be really, really difficult to do. But if you created an impact or an explosion that would put so much of like vaporized rock into the atmosphere, you would create a firestorm across the entire planet. So not to stray too far into exterminatus grade weapons, but yeah, the Lance strike isn't going to do it. But there are ways that we could definitely light a planet's atmosphere on fire in a really horrific way. The counterpoint to all of this that I want to offer you is, what's the point of the virus bomb? Because if the virus bomb was just devastation, if we just wanted to kill everything on a planet, there are other exterminatus grade weapons that we can use. There are cyclonic missiles, for example, which we just referenced. We could just bombard a planet until everything is dead, right? There are other ways that we could kill a planet. Virus bombs aren't, I mean, even in the story, they're referred to as, they are a weapon of terror. So it's not to destroy a population. It's virus bombs also render the planet uninhabitable, right? So like the virus is there latent. Conquest isn't really the goal here. We're not going in and conquering this dead rock now, and risking our troops getting infected. So it's probably not a conquest thing. It really is described in the books as being a terror weapon, that it's made to scare people and make an example of people. And so I'm going to make the argument that instant death isn't very terrifying. If I told you that you were going to die in seconds in a horrible disease, or instead die in days from a horrible disease, like dying over days is a lot worse. Not to be too morbid about it, but like being alive for hours to days while your body liquefies is a really, really horrifying and terrifying idea, especially if there's no cure and there's no way that you're going to be survive this. In fact, I'm going to offer sort of an example from a book by Gillen de R.C. Wood called Tambora. And a little bit of background on the story. Tambora is a volcano that erupts in 1815 on the island of Sumbawa, I think, in Indonesia. And this volcano puts so much sulfur dioxide in the atmosphere that it basically changes the climate on the planet, and places on land tend to get, that are affected by this plume, tend to get a lot colder. So, for example, in Switzerland, the glaciers are advancing in visibly measurable distances. Across Europe, they had basically a year without a summer in 1816, and tons of people died. In China, a province that was usually pretty prolific and produced a lot of plants or crops. Crops failed for multiple years in a row because it was just too cold and rainy. And in India, the rain and the climate change messed up the monsoons and led to, in addition to human behavior, led to a cholera outbreak. So cholera is a bacterium that lives in water and usually it doesn't really infect people, but it can undergo sort of a physiological change where it does begin to infect people. And when it infects people, it basically burrows into your stomach lining and causes your stomach to basically start to dissolve, which is really, really bad. So your body flushes it out with diarrhea. Sorry for the visual examples. And that diarrhea ends up usually going back into the water system, and then people drink the water, and then they get cholera from that infection. So that's our vector. What is important here is that you can get cholera in the morning and be dead in the afternoon, which is kind of a terrifying thing, right? Like you can be completely healthy at breakfast, accidentally drink some tainted water, and by dinner time you're dead. And so in this context, the British Army is sort of moving across India, conquering the colony there. And this cholera outbreak basically paralyzed the army. So I'm going to read this. It's a little bit long, but I think it's a good indicator of sort of the terror that we could inflict without having instant death be the outcome. So and I apologize in advance, I stutter and I'm dyslexic, so reading out loud isn't really my forte, which is why I don't do it often. But we're gonna give it a shot. So, in the early afternoon of November 8th, soldiers brought two Indian stretcher bearers to the tent of Frederick Coburn, a medical officer attached to the Bengal Regiment of Hastings Army. The men's skin was clammy and leaden, their eyes sunken, pulse almost imperceptible. When one of them vomited, the sight of the rice-colored odorless fluid prompted Corbin to seek out the superintending surgeon, who told him to break camp immediately and find safer ground. Before he could act upon this order, however, an officer in the rear guard arrived to report that hundreds of camp followers and soldiers were already dead. Or dying along the line of the march, their lips and fingers a telltale blue. Accompanied by a cavalry guard, Corbin hurried to the road where he found the Indian regiments and their followers in a terrible state. Whole families who that same morning he had seen set off in perfect health were lying dead by the streams near the road. The next day, cholera swept through the camp of the British Grand Army with, quote, indescribable violence, unquote. Between November 15th and 20th alone, 5,000 men, women, and children died. All military maneuvers ceased, and the camp transformed into a hospital and open-air morgue. An eerie quiet descended, broken only by the groans of the dying. The British kept their tents, venturing out only to inquire about the state of sick friends, while the Indians bore the biers of the dead to the river in silence. At the height of the epidemic, even these rituals ceased. Victims were thrown into ravines or brought in to the English tents and left there. The guilt for their deaths laid ceremonially at the door of the colonizing power. Many Indians blame the epidemic on the slaughter of a cow to feed British officers. In the nearby grove sacred to, I'm going to ruin this name, sorry, Hardul Lala, a deified ancestor of a noble family. Hardul Lala subsequently became one of the new popular cholera deities with the temple as far away as Lahore. By the time it was reconstituted, Hastings camp had lost half its numbers. 30,000 followers deserted, while some 10,000 died, many of them in the act of deserting. The roads for miles around were littered with the bodies of those who had not been able to outrun the Blue Death. In the commander's tent, two Indian servants collapsed behind Hastings' chair as he worked, while the general himself gave orders that in the event of his own perishing from the contagion, he should be quietly buried inside the tent so as not to demoralize the troops or send hope to Britain's provocating Indian allies that the terms of the recent treaty might be disregarded. That is a terrifying disease. that is what a virus bomb should be. We hit you with this, and within hours, thousands of your people are dying. Your army is literally running away from the disease and leaving a trail of bodies in its wake. In all directions, deserters are literally dying because they can't outrun the disease, right? That is the sort of thing that is a terrifying weapon and would be horrifying to be used on a battlefield. And we didn't have to kill people in seconds. In fact, not killing people in seconds is what allowed the disease to transmit to other people and spread in this horrifying way. If we weaponize something like cholera, right, in a let's say a microbial bomb example, that would be a really horrible way to go. So what I'm going to propose is a different sort of imagining of our virus bomb. So let's instead of virus bomb, we'll just say that that's the oversimplification. It's just like sometimes we oversimplify things in our modern day vernacular that are not, it's not an accurate representation. So let's just have it be an oversimplification. Instead, we're going to have this two-phase weapon. Phase one is our atmospheric detonation of a bacterial pathogen in growth media. So we have something like cholera that's very fast, maybe even cholera, but imagine like E. coli's replication rate. So even faster acting than cholera. We're going to dump that into the atmosphere, and we're going to dump that into the atmosphere with growth media. So we're going to aerosolize the whole thing. We're going to have thousands of thousands of billions of droplets of this material that gets spread out in our clouds. Now, clouds aren't just water and dust. There's also a lot of life in clouds on Earth. So there's things for the bacterium to infect on the way down. So as that stuff is falling, as these little tiny droplets are falling through the air, they begin to increase their population, right? And even if we're talking about E. coli's replication rate, if it takes an hour for them to move from the upper atmosphere down onto land, we're going to have a replication rates of 16 times or more. So we're going to have way higher viral or bacterial loads in these things. And bacteria could be the source of our lesions and eating through our armored seals, because there are bacteria that can eat through plastics, and there are bacteria that can eat through flesh. And so in this case, bacteria fit this role better, right? And then our phase two is our detonation of bacterial phages containing another virus's DNA. So while the cholera-like bacteria that we just dropped from orbit is definitely going to do some infections, we are also going to intentionally release a bacterial phage that infects the virus or the bacterium that we release. Now, what's a phage? A phage is a special type of virus that infects bacteria. In fact, most viruses on Earth are phages. Because there's way more bacteria than there are other things. And the reason why we want these phages to be here is because they're going to contain another virus's RNA. So this is a bacterial phage. Bear with me. So we got our bacteria. We've got billions upon billions of these bacteria everywhere, eating through armor, causing infections, causing people to fall over dead, like cholera, causing armies to break and run away, and already they're sick. And that happens within hours. Then we hit those bacterium with a phage that's going to basically infect all of those bacteria and kill them that we just released. And you might be like, well, why do we want to do that? Well, because the bacteria will let the viruses reproduce even faster than humans will. So you've got these bacteria all over your body. You're very sick. You've got lesions. Your armor seals are breaking. You're feeling sick. Your immune system's already compromised. And then all these little phages, they land on the bacteria that are infecting you. They kill those bacteria, but then they produce themselves new viruses. So inside those virus capsules that are infecting the bacterium aren't more viruses that are going to infect more bacteria. They're viruses that are going to infect humans, right? So we sort of take a phage and put like an influenza virus in there instead, which is a really dark thing to do. Now, instead of billions or trillions of virus particles, right now we've got trillions upon trillions of viral particles everywhere. Now viral load doesn't matter because you are infected instantaneously with a deadly amount of your virus. Then we have our viruses infecting the humans, and they reproduce in the human cells just like a normal virus would. And we're going to treat them like that, the virus that infects our arthropods and turns them into soup, right? So this is a really, really terrifying situation. It doesn't happen in minutes. It's not fast acting, right? We release phase one, and then within hours, within 6 hours, people are starting to die and fall over, and their limbs are blue and their lips are blue, and they know that they're sick, right? At that point, people start to panic, and your unit cohesion breaks down, and your human followers are starting to run away. And as they're running away, they're spreading the disease even more, and they're falling over dead, and they can't even make it away from the infectious sites without dying. And we've got all these viral or bacterial cells within us replicating. Then when the phase two hits us, we suddenly feel better, a little bit better, because all those bacteria are dying. But then all those viruses started infecting us, and within hours or days, people were falling over, and their bodies are just breaking open and spilling out liquid components everywhere that are also completely filled with viral particles that can go on to infect other hosts. That's a good virus bomb. Like, that's really terrifying. So I hope that you've enjoyed this kind of reimagining and kind of exploration of this. If you have, let me know, because I can do more stuff like this. These are fun to kind of discuss and bring into our stories. And we can just talk about lore too. We can just talk about sort of the storyline. So thanks very much for hanging out, and I will catch you in our next video.